We're going to analyze, using the first law of thermodynamics, some different processes that happen on a system, a simple system of a gas, when it's enclosed in a cylinder and has a piston on it that's free to move. So much like an engine, we have gas in here, and this piston can be moved up or down depending on what happens with energy and work. Now recall, the first law of thermodynamics says the change in internal energy of a system is equal to the work, it's equal to the heat added to the system minus the work done by the system. All right, but if you recall all the way back, we actually know what internal energy is. It's the total of the kinetic and potential energy of the molecules in the system. But in a gas, there is no potential energy. Now think about why. Potential energy arises due to an attraction of one object for another object, right? Gravitational potential energy is due to a force of attraction between gravity and whatever object it's pulling on. A spring's potential energy is because the spring is stretched and it's attracted back to its rest position. Well, in a solid, we have all these particles lined up because there's high forces of attraction holding them together. So there's potential energy here. In a liquid, the same is true. It's just we get less order and more random motion, but the particles are still held together as a liquid with a definite volume. But in a gas, the particles are so spread out that there are no forces of attraction. They hit each other and bounce off each other. All collisions are elastic. Kinetic energy is conserved. So there are no forces of attraction, which means the internal energy of a gas is actually directly related to temperature. So you can say this, and if you work out the math, it turns out the internal energy of a gas is equal to 3/2 times the number of moles of gas times the gas constant R times the temperature in kelvins. So that doesn't really surprise us. The higher the temperature, the more the kinetic energy, and since the only energy of a gas is kinetic energy, the higher the internal energy of a gas. Okay. So I don't know that we'll use this equation, but it is nice to know that temperature is directly related to the internal energy of a gas. Now, keep this in mind. We are going to examine 4 thermodynamic processes that could happen to this chamber. We're going to examine what happens if it's held at a constant temperature. If heat is gained or lost, we're going to examine what happens if it's held at a constant pressure, if work is done or heat or gain is lost, constant volume, all different things. So the first one we're going to start with is this isothermal process. Okay? In an isothermal process, the temperature remains constant. So the temperature of the system remains constant. And if you think about what that means, if we come back to this equation, this means, okay, so I can rewrite this. The change in internal energy is equal to 3/2 times the moles of gas times gas constant times the change in temperature. Okay, if the temp remains constant, that means the internal energy remains constant. Right? So this means delta U is equal to 0. So let's think about what happens. If I put this thing in contact with a big heat reservoir, so this has got some thermal energy. This thermal energy is going to increase the thermal energy in here. We're going to add heat. Okay? But I don't want the thermal energy to actually increase. So I said I was going to increase the thermal energy, but I'm not. I'm going to add heat to this thing without the internal energy increasing. So if 0 equals Q minus W, whatever heat I add has to be converted into work. So Q equals work. So what this means in an isothermal process, heat added is equal to work done. Now, this is if this happens at a constant temperature and temperature doesn't change. However, not all processes are like that. So next we go to an adiabatic process. In adiabatic, instead of keeping the temperature constant, what we say is we keep the heat from flowing. So no heat flows. That is, Q equals 0. So if I come back to my equation, delta U equals Q minus W, okay, this means that this term doesn't change. So the change in internal energy of a system is equal to the work done, either by the system or on the system. Now let's think of an example of this. Okay, so I go back to my chamber of gas with my piston on it. Okay, if a whole bunch of work is done on the system, and I rapidly compress this. So in order to get no heat to flow, this either has to be very well insulated or it needs to happen so rapidly that the heat doesn't have a chance to flow. So I smash this thing down really, really quickly. What just happens? I'm not allowing any energy to be gained or lost by the system, so I just did a whole bunch of work on the system, which would be considered negative work. So I increased the internal energy of the gas. Now that means the gas particles moved faster. So if you think about this, this means the work done on a system, so work done to compress the gas increases the internal energy, and that means temp goes up. Okay? And this is how a diesel engine works. You inject diesel fuel and air into this piston, into this cylinder, and then the piston smashes down on it really hard, really fast, and that increases the thermal energy so much, it increases the internal energy so much, that the temp gets high enough to actually ignite that gas without a spark, and then it explodes and it drives the piston back up. So the work done to compress the gas increases the internal energy and the temperature goes up. Conversely, what happens after that explosion? Well, that means this gas does a whole bunch of work to push the piston, and so the work done by the gas to expand decreases U, internal energy, and that means the temperature is going to go down. And this means the exhaust is going to be cooler than the gas that was compressed and exploded. And that's actually has to be true in order for an engine to do work. We always have to end at a lower temperature than we started. So the work done by a gas to expand decreases the internal energy and the temperature goes down in an adiabatic process. Now the other two processes we're going to take a look at, one is called isobaric, the other is called isochoric. And we're going to get into these a little bit. Okay, so isochoric is also called isovolumetric, constant volume. Okay? And we also have isobaric, which is a constant pressure. Now, what we want to do with these two things is we want to use them to help us understand how work, pressure, and volume are all related. Okay, so let's start by looking at an isobaric process. In an isobaric process, the pressure is constant. So let's say we have our chamber of gas and pistons up here, okay, and we add some heat to it. So we start adding some energy into the system. The pressure is not allowed to change in an isobaric system. So that means this piston is going to expand and gas is going to get larger because we don't want pressure to change, right? Remember, pressure times volume equals number of moles of gas times the gas constant R times temperature. So if I'm adding energy into it and I don't want the pressure to go up, that means my volume has to increase. Now, if we think about this, how much work did this gas do when we added heat to it? Well, let's see. Work is equal to force times distance. However, when we're talking about gases, we don't generally think about force, we think about pressure. So if the gas is putting pressure on the area of this piston and it moves this piston a distance d, what I really have is pressure equals force over area. So area times pressure equals force. If I sub that into this equation, that tells me the work done by the gas is equal to the pressure of the gas times the area times the distance that piston moves. Well, if you look at that, area times distance is volume. So this tells me the work done by the gas is equal to the pressure times the change in volume of the gas. Now, why is this a helpful thing to know? Well, let's actually create a pressure versus volume graph for this system. Okay? Pressure, volume, 0. Now, we are holding the pressure fixed. So it started down here at a low volume, say volume A, and it ended over here at a higher volume, say volume B, but the pressure never changed. Okay? And we have this relationship that work is equal to pressure times the change in volume. Well, if you look at that, that means on this graph, the work is equal to the area under this curve. And we did this for the isobaric case, but it holds for all cases. So the area under a pressure volume curve, area under PV, equals work done. Now let's take a look at how that applies to all the other cases that we've talked about. Okay? So if we come back up to isothermal, okay, remember pressure times volume equals number of particles times R times delta T, well, or times T. And if our change in temperature is 0, delta T equals 0, that means this is actually equal to a constant. Okay? Which means our pressure volume graph looks like this. We have pressure over here, we have volume over here, and the pressure times volume is constant. So we have this nice inverse relationship. So that means if we have an isothermal process and the pressure volume system state went from A to B, the work done is equal to this area right here. Now, you actually need calculus in order to do that, but you can average, you can get an estimate by using either an average pressure or by figuring the area underneath this, plotting it on graph paper and figuring the area underneath. Okay. So in an isothermal process, we use the pressure volume curve. The area underneath it is the work done. What about adiabatic? Now this one is a little bit harder because the temperature is allowed to change, but the heat is not, right? So we get no change in heat. Now if you think about what that means, if we go back to this, the change in internal energy of a system is equal to the heat added to the system minus the work done. If we are telling ourselves that the heat does not flow into or out of the system, then we have the change in internal energy is equal to the work done by the system. And so this is actually going to cause increases and decreases in temperature as well. So it's easier to think about this one in terms of pressure and volume. If I start with an isothermal process, so I'm going to draw an isothermal process like this from A to B. Okay? Now this happens if the temperature is not allowed to change, but if the heat doesn't flow into or out of it, what happens here? Well, the curve ends up being a little bit steeper and a little bit less work is done. And what I mean by that is this would be adiabatic, so A to C here. This would be an adiabatic process. Less work is done since the temperature changes. Okay? So in isothermal, the work that happens goes into, or the heat that's absorbed goes into work. But here, some of that internal energy is going to be a temperature change, and so less work is actually done. Less work done due to temperature changes. Okay? So it's a steeper curve. And then the other two are pretty straightforward. We've already looked at isobaric, where the pressure is constant. In an isochoric, where we have a constant volume, if you think about this one, volume's here, pressure's here, we can increase the pressure in a gas without changing the volume. But if you look at that, that means no work is done. Remember, work is equal to pressure times change in volume. If the change in volume is equal to 0, then no work is done. And so what happened here? Well, that if you look at that, if we go back to internal energy, delta U equals Q minus W. If there's no work done, then that means all the heat added went into thermal energy, which means this is just going to be a temperature change. Temp change only.